Okay, hello everyone. So today I'm going to speak about Agda --bridges, which is an extension of cubical, which adds parametricity primitives and equations. And the goal, of course, is to have three theorems available inside Agda. So you can do this externally, but you have to add primitives if you want to do this internally. And it's based, the implementation is based on this paper by Evan Cavallo and Robert Harper, which I call the CH system. And this paper uses original primitives from Bernard Copan and Brown. And in fact, they extend Cartesian cubical type theory, so meaning the cubes there have diagonals, but we extended Agda's the Morvan cubical type theory with parametricity. So it's a bit different in that respect. So here is the plan of the talk. First, I'm going to draw a quick comparison between cubical and bridges, because it looks very similar, in fact. Next, I'm going to talk about bridges, main primitives and equations, and I will be giving the cubical counterpart, dot Agda example, and I will say a word about the implementation as well. And I could prove a very general parametricity theorem within Agda bridges, and I try to make it modular, and we'll talk about that in the last parts of the talk. Okay, so let's start by talking a bit about cubicals. So path P is a type which grants an internal notion of isomorphism because the other primitives that cubical provides make this type former probably commute with other primitive types. So for instance, you all know the Phoenix principle, which says that the path P and the pi type formers commute. And univalence, of course, is a commutation of the path P type former and the universe, which is a closed type. And of course, we can compose those commutation principles to obtain new commutation principles. And there I just wrote the commutation principle for the type of group, which you can see there. So, of course, path at the type of group is just a bijection which respects the structure. So the cool thing, of course, about cubical is that functions become now group-weight functors, and in particular, type formers are going to preserve isomorphisms. So this means we can transport proofs and implementations along equivalences. So let's compare this to Agda bridges. So now, bridge P, it's a novel type former introduced by Cavallo and Harper, basically. And it grants now an internal notion of relation this time, not isomorphism. And I should say rather the notion of logical relation, that is a relation compatible with the structure. And if you want an example of logical relation, you can open a programming language book, and they often define those kind of relations for PL expression types. And I think the most simple cases are when the relation is actually a predicate, which respect the structure of the expressions. And similar than in cubical, the other primitives that bridges provide are going to make this type probably commute with other primitive types. So this means that this time we get a commutation principle between bridge and pi, which is called bridge Phoenix. And as you can see, it tells that a bridge between two functions is a proof that they are pointwise related. And relativity is the bridge counterpart of univalence, and it tells that a bridge at the universe is exactly a relation. So in a way, we have succeeded in internalizing relations. And yeah, what's a bridge between groups? It's actually a logical relation of groups. So something that looks like congruence of groups, except that it's not equivalent relation. Okay. So this actually turns types and functions into reflexive graphs and relators. So relators are morphisms of reflexive graphs. And in particular, type formers are going to act naturally on relations. And thanks to this observation, we are able to prove, to state and prove a first version of the parametricity theorem within Agda bridges. And it looks like this.
May I?
Yeah.
Why reflexive graphs? Are these reflexive relations or just relations?
Yes, because there is at each type a reference bridge, which looks like this.
Ah, okay.
But it's not more because you cannot compose relation in canonical ways.
Yeah.
That's different from group waves. From Eisenhower. Okay, so the parametricity theorem looks like this. So if you have a polymorphic function little f, and if you have a relation between a0 and a1, then first, so f is of type for all x, big F of x, and big F is going to act on relation, so we can put it there, like its action. And parametricity tells you that the implementation at a0 and the implementation at a1 are actually related over this novel relation, this structural relation. So this is what the parametricity provides. It provides a proof of relatedness under a structured relation. So let's talk a bit more about bridges. Actually, they work like paths with their own interval bi and the constants I named bi0 and bi1. And I was saying that you have a Raffel bridge, something that sends, right, you can introduce such bridges by lambda abstraction and eliminate them with application. And of course you have this Raffel bridge, which sends everything to A0 here. So it's a bridge between A0 and A0. And here I put the action of little f on bridges. So it takes a bridge between A0 and A1 and it produces something, a bridge between f over A0 and f over A1. And as you can see, the line argument of this bridge P type, it's not a conventional line, it's an affine line, and this is important for what follows. So this is the tick modality for guarded, from guarded cubical. And it ensures that the logic of bridge variables is affine, but I'm going to say all about that now. So let's look at the rule for eliminating a bridge. So if you have a bridge Q and a bridge variable X, you can consider Q of X only if a certain freshness condition is met. And basically this freshness condition expresses that the free variable of the bridge, so actually not the interval variable or the bridge variable, must appear before X in the context. This is the freshness condition which is raised when you apply a bridge to something. And so accordingly, when I apply Q to X and when they come in this order in the context, this is okay. But if I reverse the order, Q of X will be rejected by the guarded machinery in Agda.
So in your rule, X is a variable, but in the Agda, X can be an arbitrary element of BI, not just a variable.
Yes.
How does this reconcile? Can you apply Q just to variables? Is that the idea? Or to any?
You can apply Q to bi0 and bi1 and to variables as well. And in Agda, when you apply Q to variable, then a tension constraint is raised.
Mm-hmm. Right. What does it mean to tick an argument?
Yeah. It it means that actually, it means that stuff that comes after X will be fresh for X. And so,
should you?
no, that's the other one. So here Q comes after X, so it might not be fresh.
Yeah, but okay, so there's still a mismatch.
Between the attacking rule and yeah. Sorry about that.
But if you're not answering it now, it's fine. You can also discuss this.
Yeah, so there is another example which doesn't type check. It's there are no functions which take a bridge of bridges and make the diagonal bridge. So lambda I dot qii. This is going to be rejected by those constraints. So the next primitive is called extend, and extend provides the commutation principle between bridge and phi. And it basically tells us that if two functions are pointwise related, then they are related. So this is one direction of this bridge connect thing I was mentioning earlier. And here you can see the proof of the commutation principle, is equivalence. So one side goes by referral, but the other side, for the other side, we need the extend beta, the beta rule of extend. And it's a bit exotic as a rule, I would say, because when it fires, it needs to capture a bridge variable somewhere in one of its arguments. So let's look at the rule for a while. So you can see here the extend primitive, and this argument A depends on a bridge variable in the context. And we want to say that it's equal to something where a bridge variable X is captured. But actually, if you want this to be sound, first with respect to the CH system and second with respect to the model, we need to generate here a freshness constraint as well. And the bridge variable R, this is one of the arguments of extend, must be fresh in lambda x, that's the constraint. And because of this, when you reduce extend, since freshness is not reflected by reduction, in theory you should normalize its principal element A, but I don't do that in implementation because it's actually not necessary for practical examples. So instead, I think at worst, I reduce A. So first I try to see if R in fresh in this thing as is, and then I simplify it, and then I reduce A, but I don't normalize it because it would lead to inefficiency. So this means that the equations of extent are sound but not complete. But it's not a problem, as I was saying. Okay, and the next primitive validates the volatility principle. And here is a fragment of the proof. Right, so there is one, this is not a trivial theorem. There is one retract proof that uses a commutation principle between bridge and equivalences, which was not trivial to come up with. And actually the other side goes by computation, but it uses this time gel eta, and gel eta also has capturing happening in there. So same type of rule than extend data. Okay. So now I'm going to say a word about mixed composition design. So the bridge version of HComp. So as a reminder, HComp allows us to adjust elements of types along a partial, along a fragment of this type. So for instance, if I want to define path composition P followed by Q followed by R, I can adjust this Q on a cofibration on a subtype of the path type, which is I equals I0 or I equals I1, or in other words, not I or I. And there you can see that I specify that on the first clause of this constraint, it should be P of not J, and on the second clause, it should be R of J. So this is how HComp works. And I want to do something similar, but where instead of having path variables there, you could have bridge variables as well. And this is important, for instance, for HComp in a bridge. So what are bridge constraints this time? So if you have a set of bridge variable names psi, a bridge constraint is going to consist of such a clause. And yeah, so here's an example. You could say x equals bi0 or y is 0 or y is 1. And the idea is that you are going to be able to take unions of hyperplanes or the entire cube as well. And this is different from cubical because in cubical we have connections. So this means that we can, we can like take, for instance, a line plus a point there, and it's okay. But there we only have unions of hyperplanes. And my final, like this B const is one component of the type of mixed constraint. So what's mixed constraint? It's basically a pair of a path variable and a bridge constraint where top constraints are identified. And of course, the top constraint in I is I1.
Sorry.
Yeah.
So the big definition of BC STR,
yeah.
I don't see how this constrains with a lot. I mean, basically, you have a disjunction of these atomic settings, like a variable to a 0 or 1, right?
Yes.
Because you wrote it up in a bit of a complicated way, but
sure.
I mean, basically, yeah.
So those ORs, they are syntax, right?
Yeah. So it's a disjunction of these atomic settings.
Yes, indeed.
Yeah. But they are not disjunct. Yeah.
And having this quotient is important because we want this map embed, which sends I into I and the bottom mixed constraint, the bottom bridge constraint, sorry. We want this map to be an embedding of logics, meaning that if I have a phi which is 1 in I, and this is a cubical primitive, then I should be able to prove that the embedded constraint holds and vice versa. Yeah, and this is some primitive that I added myself. And having this embedding of logics makes basically the translation between cubical and bridges sound. Okay, so let's take a look at mixed homogeneous composition now. So it looks like HComp, of course, but you have different types of constraints. So in HComp, we specified an I cofibration, but now we specify mixed constraints, and also what I call the adjustment there, U. It's going to be a line of mixed partial elements this time, and not partial elements. And mixed partial is, this M partial primitive of bridges. And so I had to duplicate the HComp equations, basically, for mixed composition. And this time I had to propagate a mixed constraint. And I did that for when the focus type A was glue, mixed composition, part B, record, and data types. And there are no good equations for it. And the CH paper specifies rules for doing that for the bridge type, the gel type, and transporting along lines of bridges, gel types, and mixed compositions as well. And the last one is a work in progress, actually. Okay, so actually, I would say the theory is almost there. I'm only missing two things. So as I was saying earlier, extent equations are not complete, but it's not a problem in practice. And also, in cubical, when you elaborate a function that has a hit argument, it's going to generate a clause for edge complements of the hit, which are considered to be canonical elements of that type. And in my case, I should generate such a clause, but for mixed composition elements. But for now, I'm only doing that if the underlying constraint is an embedded path constraint. Like, I'm basically not doing anything. I would like my system to be able to type check cubical files, but for now, I'm not bothering with hits, basically. This could be very interesting to implement. Okay, so now I would like to explain a bit how we can obtain parametricity internally within the system. So here is the first naive version of parametricity. This is basically the triangle I was showing earlier. This thing. So the problem with that is that in practice, you start from a relation, and then you give a bridge to this theorem, and then it gives you a bridge, and you want a relation back. And we can abstract away this conjugacy and define a class of type former that comes equipped with a custom action of relations, which satisfy this equation. And so this is what I call the native relator. And parametricity is going to hold for this class of type formers. So what's a native relator? First, a native reflexive graph. It's a bit like a univalent groupoid, if you wish, but for relations this time, like for bridges. So it's a type G equipped with edges. So this is my notation for edges, and also an equivalence between bridges and edges at each G0 and G1 in G. And you might say that the type of reflexive graph is equivalent to type, but it keeps track of the mismatch between bridges and relations, so it's actually useful for doing proofs. And for instance, type is a prototypical native reflexive graph if you equip it with relations. And the proof that it's a native reflexive graph is exactly relativity. And of course, a native relator is going to be a morphism of such reflexive graphs. And now we get a new parametricity theorem. So you start now with f from G to type, native relator. So G is a native reflexive graph. And you can prove that it's native by composing basic native reflexive graphs and relators. In other words, by combining together commutation principles. And then you get, again, this parametricity theorem, but which is more general. And with that, I was able to prove several free theorems. So first, you get basic Church encodings. And so here the proof considers this type former and prove that it's a native type former by applying basically the pi, the commutation with between pi and bridge. I could prove that system F has a parametric model within, system F has a parametric model. Also, I wanted to prove that the circle has a Church encoding, which looks like this. And omega is taking a pointed type and making a loop space out of it. So path at the specified point. But for this, I think I need what I talked about hits. So it's not yet there. And also, I would like to explore other examples. For instance, I think it might be interesting to see what happens when we quantify our monads. Do we get some kind of effect parametricity? I would expect so. And also, in the CH paper, they have a proof that the smash product of pointed types satisfy associativity and the pentagon. And this proof comes for free. This is something I would like to achieve as well. It could be cool to have such a formalization. And with that, I'm going to thank you.
Can you show the first proof? The Church Williams?
Oh, yeah, sure. If I
Sorry, would it be possible to kind of like zoom in?
Yeah, sure.
Just a tiny bit?
Like
this? Awesome.
So can you explain the proof?
Yes.
So we wish to prove that bool is equivalent with its encoding, and there are two retract proofs that we have to give. So it's easy to see that bool is a retract of the encoding, but the other way around is where it's difficult. And there you have to use parametricity, of course. And as you can see here, I'm using this this param theorem that I defined in another file, and I give it the proof that this lambda dot x give x is a native parameter. But I can go to param if you want.
Right, so the bool to Church is the if basically, right?
Yes.
And then, yeah, so the Church bool relator, that's something you have to define, or?
Yes. So this is something you obtain out of bridge for next twice, because lambda x dot x times x gets x. If you want to prove that it's a native relator, you have to apply bridge connector. Like it's a composition of
Maybe
of
just
two
to
relators.
go to church pool and
Method dot.
Right.
Okay.
So it's obtained as a composition there.
control classes with the
Yep.
stuff.
Is that okay? yeah, we factorize this map there, x maps to blah, into two maps which are themselves native relators, and a composition of native relators is still native relators. You have to paste the diagrams I showed. And this is bridge next, basically.
I had another question. So you want to guarantee affinity of use of some variables, but you use this log, the tick.
Yes.
Is this essential, or is this because one could also use quantity? If we extended it with a fine quantity, right? Currently we don't talk about a fine. We just have 0 and omega, but could that also solve this, or would there be another way to encode it, or is something missing?
I don't know anything about quantities in language, so I couldn't answer.
I think the issue is that other than bridge application, almost anything should be considered additive, so you can actually almost always use bridge variables twice, except when you're applying a bridge. So you can say if it is a square of bridges, you can write that I because then you're using I twice to apply a bridge, which is illegal, but you can make, if you have two bridges f and j, you can make a pair fi, ji, because I is considered additive. So it's
okay, so it's not that simple.
no.
So the sort of top level question here, I mean, it seems that a lot of the structure is the same kind of structure as for the interval. Sort of, is this, I mean, I assume you can't just specialize this and get the interval stuff automatically, but so what are the main differences? Where is it more restricted and where is it more?
Yes. First, the affinity, I guess, of this variable logic. What else? Yeah. Second, the co-fibration logic of Agda cubical is this De Morgan algebra thing, but we have those unions of bridge hyperfaces, so that's a noticeable difference as well.
So basically, you don't have connections of bridge variables.
Yeah, there are no connections of bridge variables.
I just don't know that terminology, so what does that mean in practice? I mean,
Right. For instance, you cannot have a constraint, like if you have x and y, two bridge variables in context, you cannot define a constraint which is a line union a point. You have to give a union of hyperplanes. So y equals I0 or x equals I1. This is what the logic allows you to do. And in cubical, you could consider a line plus a point by saying, I think, not y or x and y. So you see, we have this and combined it.
and that would correspond to something which is just not true by purpose.
It's not sound to have such a logic in the bridge case. So I think you could have a reversal, maybe, but this would complicate the logic, but you could not have connections.
Because I mean, you always sort of wary of adding yet another thing which is sort of similar to another thing, and then we get the even more complicated theory.
So it was a question if one can factor stuff, but maybe
Indeed.
that's a later phase. Okay, are we good to move on to next talk? And thanks again, Antoine.